In this video, we will use combustion analysis for the determination of empirical formula. Now, combustion analysis takes some sample, reacting it in the presence of oxygen to produce, usually, carbon dioxide and water. And in this schematic here, we see that we have three modules. We have the copper oxide module to aid in combustion, and then we also have two absorbers, one for absorbing water and one for absorbing carbon dioxide. Now, if we know the mass of these absorbers before and after the reaction, we can find out what the mass of water produced and carbon dioxide produced is. Now, the basics of combustion analysis is, again, you take a hydrocarbon, that's a compound containing carbon, hydrogen, and possibly oxygen, react it in the presence of oxygen to produce carbon dioxide and water. However, for our purposes, we don't know what the formula of the hydrocarbon is. Therefore, we don't know the stoichiometry of this reaction, but that's not important. All we need to know is the mass of the original sample of the unknown and the mass of the carbon dioxide and water. Now, you notice in this example, we have more mass of carbon dioxide and water produced than original sample that we put in, which means we have added mass to our products. That's because we reacted the sample in the presence of oxygen. That's where the additional mass comes from. Now, in this example, we don't know if we have oxygen in the sample or not. Therefore, we're going to have to find out what mass is left over, if any, once we account for the mass of the carbon and the mass of the hydrogen. So first off, we need to find out the mass of the carbon and the hydrogen in CO2 and water. And we're also going to record the moles of carbon and hydrogen along the way. This is going to become important later on when we want to use the mole ratios to determine the formula. So we start with our 17.26 grams of carbon dioxide. We're going to divide that by the molecular weight of carbon dioxide, or multiply times the reciprocal. And then from the moles of carbon dioxide, we're going to find out how many moles of carbon we have. Now, the reason why we do this is because we want to keep dimensional analysis clean and tidy. So, grams of carbon dioxide cancel, and now that we know the number of moles of carbon dioxide, we're going to convert moles of carbon dioxide to moles of just carbon. Now, in this case, it's just a 1-to-1 ratio. And the reason for that is that there's only one carbon in carbon dioxide. Now, this seems like a waste of time, but it becomes important later on when we're determining the number of moles of water and hydrogen. Once we have the moles of carbon, we're going to multiply that by the atomic mass of carbon, and this tells us the mass of carbon in our original sample. Now we perform the same calculation with water, but it's a little different. We take our 7.06 grams of water, convert that to moles of water, but now we want to convert moles of water to just moles of hydrogen. Now, in the water molecule, there's 2 hydrogens for every 1 oxygen, or 2 hydrogens per molecule. So this is a 2-to-1 ratio. This is going to double the number of moles, and this is the only way to make the calculations work out. Check your dimensional analysis. We just want to find out the moles of hydrogen, and this is the only way to do it, multiplying it times the 2-to-1 ratio of hydrogen per water. Now that we have the number of moles of hydrogen, we're going to save that for later, and also convert it into the mass of hydrogen by multiplying it times the atomic mass of hydrogen. Doesn't change it that much, but these small changes can make a big difference. Now that we have the mass of hydrogen and carbon in the original sample, we're going to add them up, and we find out that, essentially, it equals the exact same mass of the sample, which means there's nothing left over. There's no oxygen present in this particular hydrocarbon. Now that we know that we don't have any oxygen in the molecule, we could take our mole quantities of carbon and hydrogen and set them to the lowest whole number ratio. Now we do that by taking each one of the values in moles and dividing it by whichever value is lowest. This sets everything relative, in this case, to carbon, the element that's in the lowest mole quantity. So if we divide both of these by the number of moles of carbon, that means that for every 1 mole of carbon in our sample, we have 1.998, or essentially 2, moles of hydrogen, which means that our empirical formula is CH2. Now we can round this 1.998 moles of hydrogen up to 2 because it's close enough to 2. If you haven't performed any intermediate rounding, all of your values should be very close to an integer or a very recognizable fraction. So be careful you don't perform any intermediate rounding. Always carry at least one extra digit beyond the last significant digit. Now, if we're given more information about our unknown compound, for instance, if we're told that its molecular mass is 70 grams per mole, we compare this to the empirical mass of our compound. So we take 1 carbon and 2 hydrogens, and we determine that the empirical mass is only 14.026 grams per mole. This is much less than the molecular mass. But if we take the molecular mass and divide it by the empirical mass, we find that we're off by a factor of about 5, which means that if we just multiply the subscript in our empirical formula by 5, we have a molecular formula of C5H10. So this is an example of calculating the empirical formula from the combustion analysis of a compound that does not contain oxygen.